Welcome class to chapter 9 on the t-distribution. So in the text they talk about at the beginning of the chapter a possible research question. You want to know whether psychics can predict the future. By the way, if they really can predict the future, why do they have to ask your name? Okay, dumb joke. But anyway, here we go. You want to know whether psychics can predict the future, so you decide to test them with a deck of cards to see if they can predict the suit of the playing card better than the statistical average. There's 4 suits in a deck of cards, so that'll be 25%. You give your sample of psychics 100 trials, and in this example in the book, and you want to analyze your results. Now you have the population mean, but you don't have the population standard deviation. Okay, their population mean symbol, right? We hopefully know that. And the population standard deviation, you don't know. So you cannot use a one sample z-test like in the last chapter. You need to use a one sample t-test. The null hypothesis, your default action in this example, people can't predict the future. It's a bunch of poppycock. Prove me otherwise, right? And psychics will have a mean score on the card prediction test equal to or lower than 25%. If you guess, of course, you'd be 25% correct. The alternative hypothesis would be, whoa, people can predict the future, right? Psychics will have a mean score on the card prediction task higher than 25%. So they'll do better than if you guessed and stuff. So here we go, talking about the estimated standard error, just a slight variation of the standard error that you learned in the last chapter. When we don't know the population standard deviation, we must use the sample standard deviation to estimate standard error. So estimated standard error, an estimate of sample error that is determined from the standard deviation of the distribution of sample means using the sample standard deviation to represent the population standard deviation, and this is the estimated standard error symbol, and it's the sample standard deviation, not the population standard deviation, as in standard error over the square root of n, which is your sample size. Book then goes into p-value, which we've already reviewed last chapter, right? P-value for our inference statistics indicates the probability of getting our t-score in the distribution of sample means if the null hypothesis were true. If the psychics do much better than the statistical average, their score will be an extreme score, right? In the distribution of sample means, it'll be a very rare occurrence. The score will be shocking. Oh my gosh, right? We expect to have scores here, right? And make our null hypothesis that people can't predict the future look absolutely ridiculous. I mean, apparently we're on to something, right? People can predict the future because of these extreme scores. The probability of getting such an extreme score in the distribution of sample means, when the null hypothesis is true, is extremely low, right? If you had all these different sample means that you gathered from psychics and the probability, or just regular people, right? The probability would be very low that you would get that score just out of just regular people and stuff, right, that can't predict the future. The score will fall in the critical region and we will reject the null. So that's the goal when you're trying to gain your proof of your alternative hypothesis, right? It's to pass this finish line, right? And that's what, are we showing proof or not? We want to pass this finish line, right? And the score will fall in that critical region and we will reject the null. Remember, the critical region is determined by the alpha level that we set, which I call the risk tolerance knob. And in the case of the one sample t-test, it is demarcated by the t-crit value, okay? And so when you get your results, I like to map it out, like chart it out, and then kind of, all right, here's my t-crit value, and then shade the region. And then it's really easy to see whether or not the psychics did better. And in this example, they did 1.42 was their t-score, but your t-crit value is 1.67, so they didn't quite pass the mark in terms of that. Looks like they did a little better, right? But didn't do better such that it was like extremely shocking and like, oh my gosh. least at the alpha level of 0.05, which we're going to go over. If the psychic scores are not extreme, they are relatively common occurrence in the distribution of sample means, right? You're finding them in there. Probability of getting this data when the null is true is high, because look at all these scores. The evidence is not shocking, but seems to fit with the default action. Then we stick with our default, stick with our guns, and fail to reject the null hypothesis, or rather say, we learn nothing. The t-distribution. Okay, here's that chart, which you'll know like the back of your hand after you finish these upcoming chapters, right? Right now we're just dealing with this area right here. We are not doing correlational studies and studying relationships. We're studying comparing means here. How many sample means? One sample mean, right? We have our sample. And is the standard deviation of the population known? Yes, then we would use the one sample z-test, right? So we basically are just learning this chunk of it right here. And if the standard deviation of the population is not known, then we will use the one sample z-test, or t-test. T-test. T-test, not z, whatever that is. Okay, t. And that repeats it right there. T-statistic is similar to a z-statistic. Maybe that's why I got confused a little bit right back there. But it's substitute the estimated standard error for the standard error, right? That is, replace population standard deviation with a sample standard deviation. And this is the t-statistic right here. Pretty cool statistic. And check out how an increased sample size will help increase your t-score. So I just have an example of you have a sample size of 50 versus 25, and what you end up having is a t-score that's higher with the same data otherwise, right? That you scored 27 on each one, and you got a higher t-score as a result of increased sample size. So increased sample size will give you better t-score, help you pass the finish line a little bit easier, right? So it looks like sample size wins, right, in terms of statistics. Standard deviation of distribution of sample means, recall. Remember, this is a slide from last time right here. I just noticed this Zerota. I'm not quite sure what that is, but I got it from online. Recall that variability is affected by sample size, and the more scores that we have in our sample, the less variability we will have in our data as the data becomes more representative of the population. And you'll remember this ball dropping experiment that I posted some videos on the Galton experiment, which you see a lot of variability here, but not a lot of variability here. Looks like a very standard distribution. Due to the central limit theorem, the larger the degrees of freedom, remember, n-1, the closer the distribution of t-scores gets to a normal distribution, okay? So that's good, right? As the psi approaches infinity, it becomes just like the z-score. The variability increases, of course, with a smaller sample size. As such, the critical region for t increases to account for variability. With a larger sample size, variability decreases, and the distribution becomes normal, much more normal. And as such, you will notice that the critical region for t decreases with increased sample size. So in sum, as you'll see through the chart, this example, if you look through the chart, right, increased sample size is very good. We will use the t-table, and it's in Appendix C in your textbook, instead of the unit normal table for z-tests. Instead of looking up a p-value in the table, we will be looking up the t-scores that border the critical regions and compare it to our calculated t-score for our sample. And I'll review that, how to use the t-table, in the next section, or in the next section, right? Not the, because, t, not z. Of course, that's the one sample t-test is what we're going to review now. Same hypothesis testing procedure. Make your hypothesis, set a decision criterion, collect your sample data, calculate statistics, and then make your decision to reject or fail to reject, or you learn nothing, right? Step one, state your hypothesis, and so the default action People can't predict the future. It's a bunch of BS. Prove me otherwise. Kind of, we already reviewed this slide, right? Alternative, whoa, people can predict the future. Psychics will have a mean score on the card prediction task higher than the 25%, which if you guessed would just be 25%. As is typical for behavior research, when we set the decision criterion, we will set our alpha level at 0.05. We will only include relatively extreme scores that are shocking and make our default action look extremely ridiculous. I like to call it our risk knob, our p-value. How much risk are you willing to make for an error? And in other words, how much are you willing to tolerate? How much risk are you willing to tolerate? You set at 0.05, we will tolerate making a false positive error, for example, with a 5% probability. So depending on the level of alpha that you set, you're going to have to get a higher t-score, right? More proof, show me more proof, or show me less extreme scores, right? Depending on the alpha level, which will increase our chance of making false positive and false negatives. They kind of go the same way, right? Anyway, as one, increases, the one decreases and stuff like that. The study collected sample from 50 psychics in step 3, so we want to collect our sample data. Step 4, we want to calculate the statistics, so we just start plugging in the data now. That's what's cool about statistics, right, is if you know what these symbols mean, you just start plugging them in. So in the book, they plugged in the estimated standard error here, and the sample standard deviation over the sample size gives you 1.41. You calculate your t-value, right? So the psychics did slightly better than the population, and then you plug in your 1.41, your estimated standard error down there. That gives you 1.42 for your t. You'll notice that I have your degrees of freedom highlighted. There are 50 participants in there. So your degree of freedom is going to be 50 minus 1, which is 49. And essentially we need our t-score and our degrees of freedom to look up the chart. Look up the critical t-value for a one-tailed test. And you'll notice here, so we want to find the one-tailed. And remember what our p-value was, our alpha value was, which was 0.05. So we're doing a one-tailed test at 0.05. So we've got this column right here. And we go down to 49, because that's our degrees of freedom. And we find the t-critical value is 1.677. If we were doing a two-tailed test, we would go to the 0.05 right here, right? Not this one right here, so this column. And then we would go down to 49 there. So notice that, one-tailed test, 0.05, boom. Two-tailed test, 0.05, boom, 2.010, right? Or 2.01. All right. So then you compare the sample t-score you got from your calculation, which was 1.42 for the psychics, right, with the t-critical value of 1.67. It doesn't really show it great in this in the textbook, but anyway, because they kind of point it there, it would be just slightly over there. But anyway, it doesn't fall in the critical region or above. Obviously, it falls below. So the sample t-score does not fall in the critical region of the distribution. Stick with the default, fail to reject the null hypothesis, or say, we learned nothing. Note the table does not provide the exact p-value as the unit normal table does. The one in the previous chapter was z-test. If you use SPSS, then you can determine the exact p-value to compare with the alpha as we did with z-test. Okay? And then also note that SPSS gives you the p-value for a two-tailed test. So to find the p-value for a one-tailed test, just divide by 2. Couple test assumptions for the t-test, the one sample t-test. The population the sample is drawn from must be a normal distribution. This assumption is necessary in order to ensure that the values in the t-table are really accurate, right? However, when the sample size is larger than 30, believe it or not, believe it or not, right? Ripley's believe it. I'm probably aging myself right there. But anyway, it's Jack Palance or something. Believe it or not. Okay, he's kind of a little weird, a little freaky, at least in my opinion. No offense if you're related to Jack Palance. Really like him for some reason. Any case, however, when the sample size is larger than 30 and the sample was selected at random from the population, violating this assumption does not change the critical t values enough to change the outcome of the hypothesis test, because the distribution will be relatively normal. So that's kind of cool, right? Better sample size helps everything. The scores in your sample must be independent observations. What exactly does that mean? This means that the scores cannot be related in some systematic way to each other. If the data of one subject affects the data you collect for another subject, then the scores in your data are no longer independent. Your sample must be chosen such that the scores do not affect each other. The example they gave in the book is being able to hear the predictions of someone else in another room that might be like, you know, the best fortune teller or psychic predictor of the future in the world or whatnot. So you just cheat off of them and whatnot. Okay, so that is it on t distribution and one sample t-test. Hope that was helpful.